In today's lesson, we're going to be looking at the surface area of prisms, and a bit later on, we'll also be looking at cylinders. Before we start looking at how to do these calculations, we need to look at a little bit of terminology. So let's look at this first bit here. It says a prism is a polyhedron. That's a pretty fancy word. That's basically a 3D straight-sided shape. And let's be even more specific, 3D straight-sided enclosed shape. So we mentioned the fact that it was a polyhedron. A really other critical thing is that it has a constant or uniform cross-section. So here we've got an example of a triangular prism. We name the prism based on the kind of cross-section that it's got. And what I mean by cross-section is, if I take this shape here, I could take a slice out of it here, I could take a slice out of it here, or at the very end, and I'll always get the same size and the same shape triangle. The way I like to imagine a cross-section is by imagining a perfect loaf of bread, one that has completely straight sides, completely straight edges, and perfectly cornered corners. If I put that into a slicing machine, I would always get the same size and shape piece of bread out. And that size and shape piece of bread, that would be our cross-section. Doesn't matter whether we took a slice of bread from here or from the middle of the loaf or the very last one, it would always be the same size and shape. It says the cross-section is parallel to two identical ends. So we've got, in this example, a square at the front, and at the back here, we've got the same size and shape square there. Same with this triangle. Here we've got a triangle at the front, triangle at the end, and it doesn't matter where we took a slice in the middle, we'd always get that same size and shape triangle out. Okay, one other thing. The other sides are rectangles for right prisms. What I mean by right prism here is that this face here and this edge here are at right angles to each other. Now we've got a bit of a weird perspective on that right angle because we're looking at a three-dimensional drawing, but that is a right angle. Now it says the other sides are rectangles. So I notice this side here, and it's a bit hard to imagine, so I'm just going to colour the whole thing in. This side here of this shape is a rectangle. So that side is sort of closest to us. The base, so if I look underneath this shape here, so I'm going to sort of draw it out here. This, the base of our shape, would also be a rectangle. And there's one more side of our shape, and this one, some people have trouble visualizing because it's trying to hide from us. This shape is behind in this direction, and that's also a rectangle. The rule of thumb for this, if you look at your cross-sectional area here, how many sides does it have? It has 3 sides. So that means your total surface area, which we'll be looking at later on, is going to have 3 rectangles. Okay, surface area. When we're finding the total surface area, we're basically going to find the area of all of the surfaces and find the total. But the thing that's really key in these questions is identifying what surfaces you're dealing with. Now, I'm going to be using things like A1, and that's just meaning an area, and I'm putting a little number underneath to say that's number 1. That doesn't mean A to the power of 1, that's a subscript. And we use subscripts sometimes in maths to just be a label. So I really recommend looking at the diagram that you've been given, and if you haven't been given one, doing a nice clear sketch of one, coming up with a plan of attack of how you're going to do the question, and then get into your regular routine of formula, substitute, answer with units. Let's get into this first one here. We need to find the surface area, so let's tell ourselves what we're doing. Surface area equals. If you wanted to put T for total surface area, that's also fine, but I just like to write surface area like that. We've got several areas that we're going to have to add together, and my trick is I want to see if I can find matching pairs of faces that are the same area. So if we look at this lovely shaded area on the bottom, can you see that that has the same dimensions as this rectangle on top? Therefore, it has to have the same area. So let's call this area 1. So for our total surface area, we're going to need 2 lots of area 1. Okay, the next area we're going to need, let's do the front and the back. So what I'm going to do while I'm explaining this, I'm going to colour in and try and colour code the areas because for some people this is really hard to visualise. So here, this is the front, and I'm going to sort of do it just lightly. That's the back. Let's call this area area 2. So we're going to need plus 2 lots of area 2. Now, we've done the top and bottom, we've done the front and back, now we're going to need the sides. So we've got this rectangle here and this rectangle here. So we're going to need 2 lots of, let's call it area 3. That seems sensible. A3. Now, of course, if you wanted to follow the rules of algebra, you wouldn't need those multiplied signs in there. So in our next line, let's get rid of them. Okay, so we've got 2a1 plus 2a2 plus 2a3. Now, just to not confuse ourselves, I'm just going to remind myself that a1 was the bottom. And the reason we had 2a1 is because the bottom and the top had the same area. a2, that was the front. I've written A2. That one was A3. I think I accidentally erased it before. So A2 was the front and A3 was one of the sides. So let's write side. Okay, so we're being very clear about that because in our next step, we need to do our substitution. Oh no, before that, we need to write in our formula. Very important you write your formula first. Sometimes it's worth a whole mark for each question. A1, that's this shape here. So that's a rectangle. So we're going to do 2LW. Now the problem is, I notice all of these faces are rectangles, and it wouldn't really make sense to write 2LW plus 2LW plus 2LW when all of those lengths and widths are different. So let's use those subscripts again. Length 1, width 1. So that means our length and width for area 2 will have little 2's, and our length and width for area 3 can have little subscripts, which are labels 3. Okay, so now we're going to substitute. I nearly forgot before. 2 times the length of 1. Now with a rectangle, which one's the length and which one's the width doesn't really matter, but I tend to like to make the longer one the length. So we'll say 1.5 times 1.0. Everything's in meters? Oh, phew, good. Okay, then we've got plus 2 times length 2. We're looking at this front face now. So let's say 1.25 times 1.0. You could just write 1. I'm running out of room, so I'm going to put plus underneath. And now we're going to look at this side. What's the length and width of this side? Hopefully you can see it's going to be 1.5 times 1.25. And, oh, we nearly forgot that 2. So plus 2 times. Okay, so let's get our calculator out. So I've highlighted what, if you were doing this by hand, you'd need to do first. You'd need to do the multiplications. I have to be very careful that I've typed this into my calculator correctly because I nearly didn't before. I missed out on this 1 here. So 2 times 1.5 times 1. You don't really need that times 1 in there because we know anything times 1 is itself. 2 times 1.25 times 1. Again, don't need that times 1. And for the last one, 2 times 1.5 times 1.25. Okay, for that, we get 9.25. Now, this is an area that we're dealing with here. So we need to put in area units. And our area units would be meters squared. We're not finding the amount of 3D space inside of this shape. We're finding the area of the surfaces. Some people like to imagine unfolding this shape into a net, and you probably remember doing nets quite a bit when you were in primary school or possibly early high school. Okay, we now have a triangular prism. We know it's a triangular prism because again, it's a straight-sided 3D shape, and the cross-sectional area this time is going to be this triangle. I've put in a side length that we also need to know for this question, so can you make sure if you've printed out these notes that you label that on? So, how many faces do you think this prism has? Well, with pretty much all prisms, provided they're all enclosed, we're going to have the two cross-sectional areas. So we've got this triangle and this triangle. How many rectangular faces does that mean we'll have? Well, our cross-section had 3 sides, so that means there's going to be 3 rectangular faces here. There's going to be this rectangle at the front, and notice this can't be the cross-section because if I took a slice of the prism here, that's going to be a very different size and shape going on there. So we've got this rectangle, and let's call this area 1. We've got this rectangle, and let's call this area 2. And then we have the sneaky rectangle that's trying to hide at the back, and we'll call that area 3. Our cross-sectional area we'll call area 4. So I like to start out with a plan of attack, making sure that I've included all of my areas here. We've got area 1. That doesn't have a matching side, so it's just going to be one of those. We're going to have area 2 and area 3. And for area 4, what do you think we're going to do with that? Well, because it's the cross-sectional area, we know there's going to be 2 lots of those. So we're going to do 2 lots of A4. Now, we need to put in our formulae. We've got all of those sides that are not the triangular cross-section. They are going to be probably rectangles. But let's have a close look at area 1. I notice that this side length is 8 meters here. What's this side length here? Well, hopefully you can see that this 8 meters is also this 8 meters. So it turns out we actually have a square for area 1. So we could write length squared. For area 2, we have a rectangle. So I'm going to put length and width, but I notice area 3 is also a rectangle. L2, W2 to match up with area 2. And then we'll have, instead of A3, we'll have L3, W3. And then for A4, we need 2 lots of, that's going to be a triangle. Remember, we had 2 ways of writing the area of a triangle, which meant the same thing. Base, height over 2, which is the same as a half base times height. I'm going to do the first one just for this example, base times height over 2. Let's get into our substitution step. So we talked before about the length and the width of area 1 being 8 because it was a square. So let's write 8 squared. What's the length and width of area 2? It's going to be 10 times 8. Length and width of area 3. Well, that's at the back there. It's going to be 12.8 times 8. Now, I wonder if you noticed with the triangle, we could actually put this over 1 and cancel off these 2 2's here. So we'd just be left with base times height. Now, I'm going to, just for a moment, erase some of my diagrams so you can have a look here. What do you think the base and the height of the triangle are? Well, remember, the base needs to be perpendicular to the height. That means at 90 degrees. And I see this lovely 90-degree sign lying down there. So this is going to be our base, and this is going to be our height. So we're going to have a base of 8 and a height of 10. And just so you know, if we hadn't cancelled off that 2, we still would have had 2 times 8 times 10 over 2. So if you hadn't cancelled that down yet, you could cancel it off here. Let's put it into our calculator. Okay, I get 326.4. What units would this question have? It's a surface area, so it's going to be meters squared. Let's have a go at this worded example here. And it's really important we read this carefully because otherwise we can make a very silly mistake. It says a farmer wishes to build a feeding trough out of steel for her alpacas. Their sketch for the trough is shown below. So we've got, this is probably called a trapezoidal prism, or you could just call it a trapezium prism, because a trapezium is our cross-sectional area. Now, the thing I know about this trapezium, which I'm going to put on this diagram now because I forgot to put it before, is this is known as an isosceles trapezium. So our cross section is an isosceles trapezium. Now you might remember when you spoke about triangles, when we spoke about isosceles triangles, they had two equal sides. Well, that's true of isosceles trapeziums. The two non-parallel sides are equal. So when this side's 16.8, this side's also 16.8. It says for part A, how much steel does the farmer need to buy? To be able to figure that out, we need to do the surface area. Now, this is a trough. So that means this surface here is not going to be filled in, or those alpacas are going to be pretty hungry. They can't actually get into it. So that means we need to be careful. We're not including every single face here. We're not going to have a top. So the surface area, if we call our cross section equal to A1, that's our trapezium, we're going to have two lots of A1 because we have two of our cross-sectional area here. Let's call underneath the bottom, we'll call that A2. So we're going to have one lot of A2, that's the bottom of our trough. Then these sides here, we've got this side and the sneaky side in the background that's trying to hide from us. These are both rectangles. Do they have the same length and width? Yes, they do. That length is this 55 centimeters, and they both have a width of 16.8 because we spoke about them being isosceles trapeziums before. So let's call the side A3. And we're going to have two lots of A3. Remember, we're not doing the top because this is an open trough. So when you have worded questions, you need to be really careful if they specify that. So two lots of A1. There's lots of different ways we can write our trapezium formula. And you need to be familiar with them and realize that they're all equivalent. My favorite one looks like this. So let's put our 2 times, and my favorite trapezium formula is H, A plus B over 2. A2 was a rectangle, so let's write length 2, width 2, meaning the length and width of area 2. And then we need two lots of A3, so plus 2 times length 3, width 3. Hopefully you can see, if we put this over 1, we could cancel down those 2's again. So when we multiply that all out, we'd just be left with H times A plus B. Now, the height of that trapezium is this lovely length here, which is 15 centimeters. So it's going to be 15, and remember A and B are the parallel sides. I like to make the smaller one A and the larger one B, but it really doesn't matter. So 15 times 30. Now the length and width of rectangle 2, we said that was the bottom. The length is going to be 55, and what's this width here? Hopefully you can see that's 15 centimeters. Now we need two lots of the length and width. We said before that the length and width of area 3, which was our side, was 55 and 16.8 respectively. Let's put that into our calculator. Uh-oh, as I was writing this into my calculator and checking my substitution, I realized I accidentally put a times when I needed a plus here. That's why it's so important to check our working out as we go. Okay, I get 3,348. Now what units would this have? Everything we had was in centimetres, so this is centimetres squared because it's an area. Part B says, how much would it cost if steel is $26.50 per square metre? Uh-oh, that's saying $26.50 per square metre, but I notice my area here is in centimetres squared. So I think the first thing we need to do to part B is to put 3,348 centimetres squared into meters squared. Now what do we divide by here? Hopefully you remember it's 100 squared. Remember 100 squared means 100 times 100, which is the same as dividing by 10,000, 4 zeros. Those 4 zeros tell us that we need to move the decimal place 4 times to the left, so that's 0.3348 meters squared. So this is a relatively small trough. Maybe it's only for a couple of alpacas. Now we need to multiply that number times the cost per square metre. So $26.50 is the cost per square metre, and the number of square metres was 0.3348. So that means, this is going to be affordable, $8.87. We need to round money amounts to 2 decimal places. Now, if this person was paying with cash and it had to be rounded, this would be rounded to the nearest 5 cents. So that'd be $8.85. The question doesn't ask for it, that's why I've put it in brackets, but sometimes it's nice to just be aware of the kinds of questions you could be asked. Okay, time for part C. Part C says if she wishes to paint every surface inside and out, what area will need to be painted? Well, we did the surface area, which is the sum of all the outside surfaces of the object. Hopefully you can see if we double the surface area, that will be like a coat of paint on the inside surfaces. We're ignoring any thickness in the metal here. So that means we're going to do 2 times our answer to A. So 2 lots of 3, 3, 4, 8. So 6696 centimetres squared. Now I realise this is a worded question, so we'd better include some worded answers here. So we would say they would paint 6696 centimetres squared. And for parts A and B, you can put worded answers for those as well. I keep accidentally cutting things out of the frame, so that's the answer to this one if you didn't see it.